Imagine transmitting 8,000 megawatts of power over more than 1,700 kilometers across one of the most demanding grid environments in the world, using a voltage level of plus 800 kV and doing it through one of the first large-scale multi-terminal UHVDC configurations ever deployed. This is the story of the North-East Agra UHVDC link in India. Commissioned in 2016, developed with ABB technology, this project was not just another HVDC line. It marked a turning point. Ultra-high voltage, multi-terminal architecture, massive 8 GW transfer capability, power supply for nearly 90 million people. Today we break it down technically, operationally and strategically. India faces a classic grid challenge. Energy resources are not located where demand exists. In the Northeast region, abundant hydro potential, remote terrain, low local demand. In northern India, massive population centers, heavy industrial loads, rapid urban growth. Transporting bulk power efficiently over long distances was critical. AC transmission at such scale would face stability limitations, reactive power compensation complexity, high losses, interregional oscillation risks. The solution? Ultra-high voltage direct current. UHVDC, ultra-high voltage direct current. Voltage level, plus 800 kV. Why is this important? Power transmitted in DC is P-Fonk Vxi. If we increase voltage, current decreases. I2R losses decrease. Conductor size can be optimized. At plus 800 kV, the system can move enormous power with manageable losses. The North-East Agra link. Rated power 8,000 nm, bipolar configuration, long distance overhead transmission, LCC-based technology. At the time, this was among the highest capacity HVDC systems globally. This is what makes the project truly unique. Traditional HVDC systems are point-to-point, one rectifier, one inverter, but this project introduced a multi-terminal configuration, meaning more than 2 converter stations connected to the same DC system. Why is this significant? Because multi-terminal HVDC introduces new complexities. Power flow coordination, DC voltage regulation, fault management, control hierarchy, protection selectivity. In LCC systems, multi-terminal operation is particularly challenging because commutation depends on AC system strength. Converter interactions can destabilize control loops. DC fault clearing is not trivial. This project demonstrated that large-scale multi-terminal UHVDC is feasible in real operation. That was a major engineering milestone. The system is based on line commutated converters, LCC. Why LCC? Because at ultra-high power levels. LCC is more mature. Lower conduction losses. Extremely high power capability. Proven technology for bulk transmission. However, LCC requires strong AC grids, reactive power compensation, large harmonic filters. Each converter station includes thyristor valve halls, converter transformers, smoothing reactors, DC filters, AC harmonic filters, reactive compensation banks. The scale of infrastructure is massive. Several challenges had to be solved. 1. Insulation coordination at plus 800 kV corona effects. Clearance distances, tower design optimization 2. Thermal management handling 8 GW continuously valve cooling systems. 3. Multi-terminal control master control coordination, power dispatch, balancing. 4. DC fault handling. Unlike AC, DC has no natural zero crossing. Fault currents rise extremely fast. Protection design had to be extremely robust. 5. System stability, interaction with India's AC network, avoiding oscillations, managing dynamic disturbances. This project reduced transmission losses significantly, improved regional grid integration, enabled renewable and hydro integration, strengthened national grid stability. $8,000 MW capacity means electricity supply for around 90 million people. It enhanced energy security, grid reliability, economic development. It also positioned India among global leaders in UHVDC deployment. This project demonstrated feasibility of a large multi-terminal UHVDC, scalability beyond $6 GeoDollar, reliability at plus 800 kV, integration of remote renewable sources. It paved the way for future UHVDC corridors, hybrid AC-DC grids, supergrid concepts. It proved that UHVDC is not experimental. It is an operational reality. The plus 800 kV North-East Agra UHVDC link is more than a transmission line. It is a demonstration of engineering ambition, a milestone in multi-terminal DC design, a backbone of India's modern power infrastructure, moving 8 gigawatts across vast distances, with precision, with stability, with ultra-high voltage. This is what the future of bulk power transmission looks like, and as global energy demand rises, projects like this will not be exceptions, they will be the standard.